I've put on the slide there, what does Iceland reveal about the Earth's crust? We've had a rift open in March after about 1,000 earthquake quite near the capital. Any of you travelled, I wonder, to Reykjavik? Series of 1,000 or so occurred quite near the capital, Reykjavik, on the west side. It's still going, but it's more or less a series of geysers, or geysers if you wish, and one vent still going. Now, it's not smoking severely. It's quite near the airport too, between the airport and the capital. The point is, however, that Iceland has been expanding, and if the original settlers there in 874, Norsemen who came there, had put a peg in near this west coast and another one on the east coast, they'd be able to show us that Iceland has expanded by about 20 metres in that time, in about 1,000 years. Now, that's quite a relevant thing, but of course, nobody's bothered to do that. But in the early years of the 20th century, before the First World War, meteorologists working on Greenland, particularly Wagner, did a scientific paper demonstrating the prospects or possibility of the Americas separating from Europe and Africa because of the similarities of the coastline, which had been known for 50 years or more, been recognised and discussed as the possibility that continents had drifted. He compiled evidence and suggested that there was paleontological evidence from various reptiles which occurred on the southern continents, and it was known that there was some evidence of an ice age a very long time ago, which we now know to be well developed at Hallett Cove, and is expressed or seen in both South Africa, South America, and also in India. And that was some 280 million years ago in the Permian period. We have the flora in our coal seams of Glossopteris, and that's known across all those continents in coals that were formed in front of the ice sheets. So he had evidence enough that the continents may well have been together. Even by the early part of the 20th century, it was realised that there was a core to the Earth and that the ocean floors were of different composition really to the continents, that the continents were lighter material. Since then, we've appreciated that there's a whole zone that extends down into the upper Earth's mantle. It's about 100 kilometres thick, that is rigid enough to be moving all the time and cracking as distinct from the material underneath it in the mantle, which is capable of flow and convection currents from the very hot core, which essentially can move things about. I suppose if we look at the southern portion of our continent, in exaggerated relief, of course, we can see that Tasmania and the southern portion, or Victoria essentially, stand like a floating mass above the deep ocean floor in blue. And there's quite a steep margin of our continental slope separating it. The various areas I've outlined in black there, Gippsland Basin, the Bass Basin, Torquay, Otway, and our own Gambier Basin up in the top left, and of course the Murray Basin just north of the Grampians, marked as GR there. So crust is distinctly different from ocean floor. It's now known that the crust's average composition is a bit like a granite, quite a bit of silica involved, whereas the ocean floors have much less silica and are more like basalt. Well, then we also notice from the distribution of earthquakes that you might define what you might call the plates. Earth's plates are well defined by the incidence of earthquakes, shown here in little red dots. They're very prominent, of course, around the Pacific Rim of Fire. They break up significantly on our northern margin, where Australia actually is pushing northwards, and the Pacific Plate is pushing westwards, hence massive earthquakes on the western rim of the Pacific Plate. However, through the central regions of the oceans, we can still see well-defined by the red spots, breaks, which represent plate margins. And so this distribution of earthquake locations led to the hypothesis of Earth's crustal plates. And the mapping of the ocean floors shows that there's some 50,000 kilometres of ridges corresponding to these rather less obvious plate margins that run through the central portions of oceans. And they're well known to be sites of active volcanism, but well hidden from view. So if we look at Antarctica or the southern pole, we find that the plate margins are well separated from continental margin. And in the southeastern corner, if you wish to say, or the bottom right, you can see there's some 4,000 kilometres of ocean between Australia and Antarctica. And that is distinctly different material, that oceanic crustal material, to the continental masses that sort of float on that. Now, how is it these drifted apart? We now have evidence that the breakup between Australia and Antarctica started about 100 million years ago, but really only got cracking about 60 million years ago, about the time dinosaurs, well, they were extinct by then, some 5 million years or so. And of course, dinosaurs are distributed across all the Gondwana continents, which are here shown well separated from Antarctica, and they're known on Antarctica. In fact, the Antarctic ones are more like South America and New Zealand, I suppose, than they are Australia. But even our dinosaurs have very large eyes and appear to have existed perhaps in six-monthly darkness. So it's a pretty extraordinary situation, and we see our continents have somehow separated and formed ocean between them. Well, we can put an analogy there to pack ice on the Weddell Sea, perhaps, and you can think of an encampment on the ice there being a continent, being carried passively on some plate that's floating by expansion of the oceans. We were just discussing the way that plates open, you might say, by narrow leads of ocean forming, and as that ocean expands, so the continents break up and separate. In my analogy here, a little encampment with 3 or 4 things like a tank and a tent is being carried passively on a plate, which may grow and enlarge in the wintertime, shrink in the summertime, crash into its neighbours, open new leads or close them. And that's the way the continents tend to behave. Now, the Australian plate, surprisingly, more or less does include India, but not so much Arabia, as I drew this figure 20 years or 25 years ago, and we now know we're separated from Arabia. And there's a new break appearing mid-Indian Ocean, which looks as if it'll separate us from our recent movements together with India. If you look at that dashed line in the middle of the Indian Ocean, that's where the tsunami occurred in 2004, where that impinges on the blue boundary to the north. Now, the colours blue are where the plates are crushing together, and the colours red are where plates are spreading or new leads are developing, you might say, in this pack ice of the oceanic crust. Right, thank you. So it's been noted that there's a mid-oceanic ridge running around these zones in mid-ocean that represent the plate boundaries, and that those are active volcanic ridges. There's only one place in the world where we actually see this phenomenon, and it's not only one place, but Iceland is the best place in the world to see an example of the mid-ocean ridge. And hopefully, if I didn't change my patterns, I did. In the Cold War period, post-World War II, a lot of work was done on the ocean floors, and that's when this central ridge was discovered. But the reason for doing it was magnetic studies to try and clarify the identification of submarines. And they found that the seafloor was actually magnetic, and that there were parallel stripes of reversal of the Earth's magnetic, they only understood it then to be the rocks, were symmetrically in a series of patterns of reversal. Sometimes north was north facing and south facing, north facing, south facing, and this was symmetrical about that mid-oceanic ridge. It's very complex in detail, but of course, once discovered, a lot of work was done on it. Finally appreciated that Earth's poles were flip-flopping in an irregular fashion every few million years, and that this was reflected in the formation of volcanic rocks. And they'd come through in that central ridge area, perhaps magnetized with north facing north as we know it today. There would be separation of the plates as they were pulled apart, you might say, by friction from convection currents underneath them. And that if the poles switched, you'd get a new zone of rocks, not perfectly even as shown in this diagram. This sort of zebra patterning was characteristic of all ocean floors, outstandingly so. It became the point that they could, when we were able to date rocks very readily in the late 1960s and 70s, we were able to, geophysicists were able to identify both the age of these bands and match them ocean to ocean. So they began to get a story for the rate of separation of various plates and how plates reformed. Now, this is the pattern. You can imagine there's some sort of convection current system going in the more mobile portion of the mantle, and that this has a frictional drag on the brittle crust above. It's about 100 kilometres down that plate margin is, the brittle crust is moving, and or in theory that it is moving, and you have central volcanism going on all the time, and that is gradually moving away from the central axis in parallel bands. And of course, if you change the magnetic sense of the Earth's magnetism, then the rocks reflect that. Now, that's a separate lecture, I suppose, but you'll see up there on the right, I've got a continental fragment in yellow sliding away from the central axis. And the continents are quite passive in this action. It's really the ocean floors that are doing all the work. There's that pattern again with the magma or the molten rock rising, and the lithosphere, or that's the litho meaning rock, the hard sphere, which is 100 kilometres thick or so, is moving away. And that includes a portion of the upper mantle and the more rigid oceanic crust. The whole of this is referred to as the lithosphere, another term for the underlying more mobile portion of the mantle, known as the asthenosphere. But it's a peculiar phenomenon which we can only imagine. The phenomena goes like this. You get stage one at the top, where perhaps you have a thing like the Rift Valley of Africa today, and then it gradually widens to become something like the, well, I've got here the southern Atlantic Ocean with South America and Africa. I was perhaps going to say the Red Sea, and then it widens further and becomes a Persian Gulf, or in fact, a Southern Ocean like we have today between us and Antarctica. And we can see this today in this area of the Dead Sea is obviously a newly formed rift. The Red Sea is a little more advanced. The Med Sea is actually probably an ocean that's closing rather than an opening ocean. Africa is crushing northwards towards Asia, and we'll do that sometime in the future. Too much for this discussion today. If you look at the big faults, you might say, of the East African Rift Valley that separate the Somalian or Tanzanian plate, which is forming today. Ultimately, an ocean will extend down from the Gulf of Aden and the Red Sea to Lake Victoria, and that may well expand, sending Tanzania eastward into the Atlantic may even close the Indian Ocean, not the Atlantic, but the Indian. So it's an extraordinary potential for the next phase of our globe. And the same sort of thing is what started the movement between Antarctica and Australia 60 million years ago. This has been going on for 10 or 20 million years already, with a triple point in the Afar Triangle, where Gulf of Aden, the Red Sea, and the Rift Valley meet. That's very typical. It's a bit as if Tom Thumb was sitting underneath and stuck his thumb up the middle of the pie, and the cracks occurred in each direction. You often get that phenomenon of triple points. And we can see again Gulf of Aden, Red Sea, and the Afar Triangle region, which is an extraordinary one. I don't know if any of you have had the opportunity to visit Ethiopia or those areas of the Danakil Desert, but there's more than a kilometre thickness of salt there, for example, which has been gradually seeping in from the Red Sea into a subsiding area, evaporated. Thing is repeated and repeated to the point that you get enormous thicknesses of salt. That's quite a common phenomenon in coastal margins. All down the Atlantic coasts, both sides, you get extraordinary thick salt deposits in the deep submarine basins. Now to look at our southern Australian plate, southern portion of it. The red line, of course, is this mid-ocean ridge where spreading is occurring today. And Australia is moving northward at as fast as our fingernails grow, 6 or 7 centimetres a year, so that you can't have a fixed point on the Australian continent and say that it's in the same location. It's moving in reasonably rapid tectonic rate, as we would refer to it. Here, I show the bands of age, not so much of magnetism in this case. It would be much more closely spaced lines if I showed the reversals of Earth's magnetism. But in this case, the bands range from about 5 million or present day spreading right in the central on the red line, and 30 million years or so in the yellow areas, getting to 60 million years where it's a light green colour. And that's the ocean floor that's been formed in this period from a spreading ridge in the centre. And it has resulted in the movement and separation of Australia from Antarctica. Same thing has happened all the southern continents. And you can actually trace other activities in the ocean floor when rocks are dated. And you'll see to the right hand margin, I've got 80 million shown on brown rocks there, and they occur again up in the Indian Ocean off our western border with some even older rocks, about 100 million years. It's rather extraordinary when we look at the globe that there don't appear to be many oceans older than 150 million years. The ocean floors are all young relative to the continents. I mean, if you look at that 100 million year old green material, perhaps a little bit older, 150 at its oldest against the Australian margin, they abut rocks which are 3 billion years old, 3.8 billion years old, even 4.2 billion years old in the purple area of the West Australian Shield. So the continents are actually very old relative to the ocean basins, which are forever changing. And next lecture, we'll talk about how oceans disappear, because the whole story of the globe, fortunately, has been one of cycling, rather like, Earth's great recycler has been the formation of new crust in the ocean centres and the disappearance of the older crust in some magical way, which is next week's discussion. The mechanism that drives that, we have right in the centre there, the mid-ocean ridge, and there's a certain pull from the slabs because, in fact, they tend to slip in underneath other areas of crust, particularly continental crust, which doesn't want to subduct or to disappear into the asthenosphere. We can see on the right there the ocean trenches, such as we get, I'll call it the Java Trench to the north of us. Very severe ocean creases or depth in the oceans there, where the plates are sliding down into the mantle. And there's a pull results, which keeps the separation going on at the ridge. And it's also driven by the convective friction, you might say, from heat rising from the outer core and spreading out laterally away from the central ridges. Earth's plates are constantly changing. To understand the migration of continents, we've got to decipher the origin and growth of the new oceans. That's the point we've just discussed, I suppose, and the fact that they expand from the central spreading ridge. Continents are carried passively away from this newly formed plate margin. And next week, discuss how the oceans disappear. The history of Earth then is the story of opening and closing of oceans. I have another break there for questions.
Yeah, just one question. What makes the ocean floor so magnetic? I presume that's iron content, is it?
Very good point. That's perfectly true. Very fine crystals of magnetite occur in the basalt, which is what is erupting in central sea floor. And these just settle like tiny magnets. And the north-seeking pole of those little crystals all statistically point in the same direction, such that the rock develops a magnetism in itself. And that's what's measured by the magnetometers taken in ships and towed behind sometimes to get a detailed map of the ocean floor magnetics. Does that help well enough?
Yes, thank you.
It happens in sedimentary rocks too, that any magnetic fragment, again, mostly magnetite, will just settle like a magnet into the sediment. And surprisingly enough, they even settle at the, what could I say, the azimuth or the angle that the Earth's magnetic lines of force are coming out of the, from the surface, you might say. And that is actually the latitude. And you can tell the latitude at which a rock is first crystallized, if it's a volcanic rock, or where it was deposited as a sediment, from the angle or the statistical angle of all these tiny magnetic fragments.
No, that is interesting.
So at the north and south pole, they'd be vertical, and at the equators, they'd all be lying horizontally. Whereas at 10 degrees north, 10 degrees south, they'd be correspondingly averaging out with a 10-degree angle to the sedimentary layers.
Oh, very good.
And that way they get up a picture of where continents were, and it adds to the story of oceanic growth. And in one way or another, you can picture back billions of years, would you believe? And it tends to show that continents come together and then separate in a sort of symphony. Every 500 or 600 million years, it seems that the continents coalesce and then separate, taking a few 100 million years to separate and then a few 100 million years to come back together. And why that's so is hard to explain. But certainly when you have a big mass of continents together, heat tends to develop underneath them, like Africa today, and it will then bulge and crack and break up into these triple points, and the bits then separate away from that original centre.
Right, okay. And
we have names for the various supercontinents. In fact, we've got the name for the next one. Everything's aimed at going towards Hong Kong. The North American continent's moving to close the Pacific, we are moving to close what there is of the Pacific to the north of us. We'll crush up that direction, and various pieces of Africa are moving across in that general direction, particularly if Tanzania forms an ocean. It'll move across presumably and weld on to Indonesia. They've named that one Amasia for America and Asia. And the last one we know, Gondwana, which was part of a huge supercontinent, Pangaea. We were only the southern portion, the Gondwanan continents. Prior to that, the Rhodinian supercontinent existed about 1 billion years ago, and Australia has one of the best records in the world of that. The Flinders Ranges are really the continental shelf of the Rhodinian supercontinent that started to break up about 700 million years ago. And there were great world ice ages then that we've got recorded extremely well, named around the world, I might add. For example, when I was in Greenland, somebody proudly pointed to me that this was the Sturtian glaciation, named from Sturt Gorge in Adelaide. And
really?
So
Wow.
I carry on, I'm sorry. Any other question? So that's where we were before with our Southern Ocean. And again, in a very approximate way, I've put the ages in millions of years. I use that abbreviation MY. Geologists tend to use capital M, small a, million N. I use MY in lowercase just because it seems more like million years to most people. But so current spreading going on in the central area between Australia and Antarctica. The older bands of rocks go through to clearly to 60 million years. And there was an extraordinary period shown in the hatchet looking green stuff when we had our Rift Valley, rather like the East African Rift Valley today. Dinosaurs would have roamed around that from before 65 million years ago. And hence we get a few along our southern coastline, but we get more in the central basins that we know of today in Queensland and elsewhere, but certainly along the Victorian coastline, dinosaur remnants are found. They're also found in New Zealand. I think I mentioned before, the New Zealand ones are actually a bit more similar to South America. And New Zealand there is shown to have separated between 80 and 50 million years ago. You think there's a little discrepancy in the colours there, but that's just something I'll quickly put onto the sheet. Now, our northern boundary, which we'll discuss next week, is just part of the rim of fire. When we look at the red lines around there, I won't go into great detail now, but there's a subduction trench marked up in the Java area. I should have put it further south. That term subduction trench is actually where the blue lines, the oldest crust, starts to disappear under the Indonesian island arc, and you get all the volcanoes resulting from that. We've got just a little click there on the changes. So there's a huge crushing zone across the so-called Alpine Himalayan belt shown in green there, where plates, they're really the Gondwanan plates, are pushing northward at the Eurasian plate, which is the biggest, really. It goes from Iceland, or the central Atlantic Ocean, right across to include portions of Japan. And interesting enough, the American plate goes north from Japan through Siberia and across the North Pole and out to include Greenland. It's an extraordinary plate boundary when we think of it. So if we look about 100 million years ago, we were in that rift phase, and there were lots of volcanoes along our Otway coast. There were some out there in Central Australia in the Eromanga Basin. That may well have been a rift trying to occur, which would have fixed us for COVID, because New South Wales and Victoria would be somewhere out in the Pacific and part of Zealandia today. Zealandia, they claim to be the 8th biggest continent. That's the New Zealanders, of course. But it's been teased out so that the continental crust is very thin and broken up into a Lord Howe Rise and a Norfolk Ridge. And of course, the New Zealand blocks of today, part of the South Island of New Zealand is not actually on the Australian plate. It's on the Pacific plate and is a bit of a stranger to us. I just put that one in to show where the mid rifts were again at about, I haven't got the age apparently, 45 million years. I believe we would have been a little bit wider separated at 45 million years, but that's someone else's work suggesting that we had a well-developed ocean, probably like, or even wider than today's Persian Gulf. And this is a period of quiescence in that there was not much material derived from the continent going into the sediments. We got a lot of limestones. So Gambier limestone started to develop a little bit younger than that, but Blanche Point marls and various other things were deposited in a situation like that. So also were the limestones of Pancake Rocks in New Zealand, for example. It seems it was a reasonably quiescent period with a lot of limey sediments. And here I've thrown in sometime in the future, perhaps 100 million years, we'd expect Australia to cross the equator. Not quite sure why the equator is given at that angle here, but Australia will expect it to crumple up a huge Himalayan mountain ridge in what is today Southeast Asia. America too may close the Pacific and dock against Asia. And that's why we use that phrase, supercontinent Amasia. I've just got some pictures here of Iceland. The North American plate, Eurasian plate are separating through Iceland, and that's where we get a classic example of the mid-ocean ridge. That's the mid-Atlantic ridge in this case. And down near Reykjavik in the southwest corner of Iceland is where that volcano is currently active. And this diagram is much older than that particular volcanism, which hadn't been known for 700 years or so. But of course, there are 30 or so active volcanoes on Iceland. And if that's typical of the mid-ocean ridge, one can see why Iceland's expanded this 20 meters or so in the last 1,000 years since settlement 874. Krafla up there is a dangerous beast. We haven't heard from him recently. The ones that have caused disruption of the air traffic are more central in Iceland there and erupting underneath the central ice cap. Krafla could be a very violent volcano should she decide to erupt sometime again, because geological history demonstrates that it was a very, very explosive volcano. Now, extending the earthquake phenomena, which probably indicate subsea volcanism. You can see the mid-Atlantic ridge going to the south there and off to the north also. It's just fortuitous, the shape of Iceland, which is all built up really of either submarine or subaerial volcanic material. Well, Surtsey developed just off the southern coast of Iceland, of course, in my early years of geology. So it was a volcanic island that arose from the sea. I hope some of you have had the opportunity to visit Iceland because it's a magnificent experience. And the very first parliament held there around the year 1000, well, that might not have been the date of the very first parliament, but I think in the year 1000, they actually decided in a parliamentary session in this rift, which met annually, to go Christian. So the country has a very long history of Christianity. At that stage, they had started the settlement on Greenland. But of course, that closed down as the Little Ice Age came through after a few hundred years and no longer was a settlement. And anyone living on the island apparently perished on Greenland, I'm sorry. but that's incidental. I don't know my stories too well. But there was a woman who was born, I believe, in Iceland, lived in Greenland, had a son in what we believe today to be Newfoundland, and then went to Rome and was introduced to the Pope in about 1006. That's an extraordinary story, isn't it? That's just a brief summary that happened this year from the 20th of March. The magnitude 4 earthquakes 3 days previous to this shot. Wow. And then that was what happened within a few days. In the previous week, quake magnitude 5.7. Now every point, now 5 to a 6 is 10 times stronger. So a 6 to a 4 is 100 times stronger. It's a sort of logarithmic scale. And 10,000 tremors recorded recently. Goodness gracious me. That was taken off the web just after the thing erupted. And the first settlement by the Norse was right near that in 874 AD, but it had not had an eruption for 700 years. Anyway, and there are some shots again from that same earthquake. I don't know why I put that bottom right one in. I don't actually register it too well, but we can certainly see an exaggerated vertical scale apparently on the left one. Surprised, I don't think that had quite that relief, but a series of centres developed along a linear rift, and many of them have quietened down now to be only something like that. That's a more recent view at the bottom, but they say 55 million cubic metres of basaltic lava. It's now in a geyser stage activity, but that's probably the phenomena that we see on the ocean, we do not see on the ocean floor. I might say too that many of our mineral deposits, particularly lead, zinc, copper, high-grade deposits like, say, Rosebery in Tasmania, are formed in those mid-oceanic rift zones because there's an extraordinary amount of scavenging of heavy metals and incorporating them in little geysers and things on the sea floor, which are known as black smokers when they're seen from, you can imagine on the sea floor, those would be almost little turrets quite often, forming mineral accumulations and concentrations on the sea floor. And that's 14th of September 2021. That's not the same eruption, but another one on Iceland previously. There was a very big one in the late 1700s that caused an enormous problem of famine and years without summer in the Northern Hemisphere. Big volcanic eruptions have that phenomenon. Normally the surface of the lavas on land look ropey and something like that. You notice that's red hot lava taken in Iceland on that Surtsey Island that came out of the sea. But I think when they're subsea, they form pillows. So large areas of various countries, Oman particularly, where I went about 3 years ago, North Island of New Zealand, are actually oceanic sea floor that have been pushed up above sea level, and they have these pillow-like forms. What happens is the lava bulges out from a crack in one of the other lava tubes or from a source, and then gets quenched suddenly by the ocean, so that the bulb or the pillow is a quenched phenomenon, often with little bubbles of gas around the margins. And many, many rocks, particularly those, say, in the nickel belt of Western Australia, ocean floor basaltic rocks, quite obvious from that sort of pattern. And I suppose I'll pop this one in. Again, this is sea ice, but I think the continents probably look like this. They've got older sea ice incorporated in younger ice as the seasons come and go. And so as the supercontinents come and go, you'll get fragments such as our Gawler ranges, as distinct from our Broken Hill O'Leary block. And then further in, you get another one, the Centralian block, or to the west, the Yilgarn and Pilbara blocks. And these can all weld together again and give you a very cosmopolitan looking continent. Not so the oceans. They're new and simple unless they disappear. Ooh, that's again another view in northern portion of Iceland. I imagine those eruptions are a bit like our, that's not northern, it's actually west central Iceland. But I imagine that's a bit like the eruptions here at Mount Gambier in years gone by, probably only 10 or 20,000 years ago. And these likewise may well be that sort of age, although there was a recent one recorded, which were so-called MAR eruptions, M-A-A-R, name coming from Iceland, where they have a lot of ash, very explosive, a lot of ash, but don't build a particularly big cone. And that's usually because they're coming through groundwater and the rock's pulverized in the act of boiling the groundwater. Another view on Iceland, that's my wife, Kay. When basalts solidify from the melt, from a thick body of molten rock, they cool at both surfaces quite often, and you get cooling columns formed through them, rather like organ pipes, and they're hexagonal quite often, or roughly so, in cross section. And this is just a very excellent example of columnar basalt. We can see this at Portland, for example, in basalts that occur there. Huge zone of columns there, radiating in various directions around what was presumably a subterranean lava tube. And it's closed off now by the sea entering it. But these radiate because the cooling surfaces were more varied here. Just to finish, this is the major rift where they held their parliament in Iceland, Thingvellir. You can imagine this filled with tents and troops at the year 1000 deciding that they'd form a Christian community. Today, they claim you can stand here, and in my case there, I'd be putting my right leg onto the American plate and my left leg onto the Eurasian plate. And so spread myself halfway around the world. There's a comment here that the basalt columns look like the Giant's Causeway in Northern Ireland. Yes, so finish this off, I think. Right, and unmute all, I guess. If I go over to mute all and mute all current participants, no. It's a free for all, I believe now, isn't it? No, I see you are muted. So unmute yourself. Yes, there's Suzanne. Suzanne, do you have a question?
I've got a comment. It was fascinating, Bob. Thank you. I've always been interested in geomorphology, and you gave some very succinct definitions of how it's all happening, and a lot of stuff that I'd not heard before. So I'm looking forward to the next 4 weeks. Thank you. It was wonderful.
Well, I do thank you. I felt a bit nervous today, which is not normal in my U3A talks. I'm okay, but I'm so worried about technology. Thank you.
Well, you mastered it very well.
Rosemary, did you say something then?
No, that was me. I said you mastered the technology very well. I didn't.
Stuart did for me, but I'll get another lesson and make sure I join. Will you be on the lessons, Lindley?
Yes, I will.
Very good. And anything there that seems to need further discussion?
Yeah, just one question. You said that, you know, sometime in the future we're going to have another supercontinent. but you also said that the oceans will disappear. So what did you mean by that? The water will dry up, so we'll have a supercontinent not surrounded by water, or what was the intention there?
Yes, thank you. A good question. The continents do crush together. For example, think of India moving across the Indian Ocean in the last 80 million years or so. It's come from Antarctica and more or less from the southwest corner of Western Australia and crossed the Indian Ocean, or the plate has carried it northward and crushed it into Asia, or Eurasia, and formed the Himalayan mountain chain. So too, Australia is starting to form a mountain chain in the Owen Stanley Range in Papua New Guinea, West Irian as well. And ultimately, we'll push everything as we close up oceans like the South China Sea, and China will find its mid-ocean airports and things are setting up at alpine heights. So if we push them into Asia, there will be presumably a dry continent, and the oceans that opened it will have closed the Indian Ocean.
Right.
That's what we'll discuss and further. We'll get on to about our fifth talk, and we'll find that there were 3 previous Indian Oceans, and they're all crushed into Asia today, and blocks possibly that came off the Kimberleys are to be found way north in the Tian Shan Mountains in China. Unbelievable.
Yes, incredible, isn't it?
Mm-hmm. Anything further? We're doing very well, right on the nose at the moment.
Yes, that photo you showed with your wife, do they know why those columns sort of form into hexagonal shapes?
Well, I think it's cooling from, you might say, a central spot. And, well, they could be circular, but that's not likely to happen. And the nearest thing, I guess, is to break up into polygonal blocks on the top and bottom surface. And those cracks tend to extend all the way through, I guess, very much like mud cracks. When you see a dam dry up, you do get these pseudo-hexagonal shapes.
Yes, yeah, okay.
All good?
All good.
Right, well, thank you very much for your attendance, and I hope we see you next week, same time, same station.
Okay, thanks very much.
Oh, thanks, Bob.
Yes, cheery now.
Bye, everybody.
Cheery now.
Right.